Another application for the cellulose is in gels, in paints, in different cosmetic products and drugs. If one disperses the cellulose by applying an excess of energy, the fibers are dispersed throughout the volume of the liquid, and then they form very, very firm gels at very, very low cellulose contents. And these gels, they have very good properties because they can be, their rheology does not change with the temperature, so they can be used, for example, in yogurts, in ice creams, in other products. They are not sensitive to other salts and electrolytes present in the formulation, so they are perfect for cosmetic products, pharmaceutics, in which you usually have a lot of other salts which can influence the properties. It can be used as a dispersive aid in paint. As we moved further in the different applications of this material, we came up with the idea of making the cellulose conductive. And usually cellulose is considered as non-conductive. And we wanted to use the large surface area that we have. And we coated the fibers individually of this cellulose with a 50 nanometer thick layer of conductive polymer. And to give you an idea, it's 50,000 times thinner than a human hair. And the product, these fibers, then they were molded into paper sheets, which you can see on the graphs. So it's just black paper sheets, macroscopically, nothing special, mechanically robust. But they possess very large surface area, and then they behave like a metal in the sense that they can conduct electricity, and they can be used in very special applications. And these applications include many different ion exchange membrane solutions in which you can just take the paper, use it as an electrode, dip it into a solution from which you want to extract something valuable. So you put the paper in the solution, you apply current, the ions are being taken up inside the paper, you remove the paper, put it in another solution, apply current of opposite magnitude, and by that release, so one can extract inorganic ions, one can extract organic ions, and we are working very hard to extract biomacromolecules. So what we want to do in the future is to be able to extract large DNA molecules and stuff and design different diagnostic setups or other ion exchange membrane solutions for biotech industry. Another application that this material could find use in is the batteries application based on paper, non-metal components. And the resultant battery setup is an all-polymer, lightweight, flexible. It's based on water, it's environmentally friendly, and it's disposable, which is a very big issue with all the battery solutions present today. There is other applications in which this material could be used, like gas sensors or moisture sensors, diagnostics, etc. So how does it work with the extraction of the different ions? As I mentioned before, we apply current to the piece of paper. We create charges on the conductive polymer, and then the ions are coming in. And then we can just remove the paper. Either we can dispose it, we can burn it, we can put it in another solution, and then release the ions. One application was the battery application, and this has come only a month ago in Nanoletters journal, and it happened to be the second most read article at Nanoletters for the past month, and there was very big interest from the media, which was very surprising to us, and there was more than 1,000 articles in the media that came out, like at the MIT Technology Review, The Economist, and and people like it, and then they like the idea that it is environmentally friendly, it's paper, it consists mainly of non-metal components, and it's water-based. So the idea behind this battery cell is extremely simple. We have two identical pieces of the electrode material that I was talking about, and they are separated by a filter paper soaked with salt. So the name for this battery, this is not something that we have come up with, but it was the journalists that came up with. They called it the salted and paper battery. And because we use the same material, both as a cathode and anode, this also makes it very simple for the production. And how we obtain the difference, potential difference between the electrodes is simply because one of the electrodes is in the oxidized state and then the other one is in the reduced. In simple terms, one is the plus and then the other one is minus, and it's identical, and it's all paper. So the only metal component is the current collector, which was the platinum foil that we used. So there is a very big interest in these kind of solutions for the future, and we are very optimistic to develop this very simple and we believe elegant solution also for the future. And what is good with this battery is that you can charge the battery extremely quickly, and this is thanks to this very, very thin coating of the polymer we have. And this battery can be charged like in several seconds, compared to lithium-ion technology today, which takes at least 1 hour to be charged. And the properties of the battery are also good because it has very large capacity and it's a stable system too. So we would like to really see something come out of this in the future and become a product. So the conclusion is that though generally mentioned in a negative context, due to environmental problems, the cladophora algae are actually an unexploited source of very highly useful cellulose material, which cannot be obtained from other sources. And this is a very good example of how people can take something bad and turn it into something useful, which is very, very rare.
Thank you. Thank you, Albert. I was sort of surprised that you were not surprised.